explore an example to better understand the concepts. Let's start. First, we need to determine the higher derivatives of a function. What is derivative is? It is the rate of change of a function represent the rate of change of the derivative f prime of x with respect to its input variable x. Symbolically, we write f prime of x is equal to d over dx times f of x. The higher derivative of a function represents the rate to the input variable x. We can denote the second derivative of f of x as follows. F of the second derivative of x is equal to d cubed over dx squared times f of x. Similarly, we can denote the third derivative of f of x as f third derivative of x is equal to d cubed over dx cubed times f of x, and so on for the higher derivatives. Each new derivative represents a higher order of change in the function. Let's take a look at an example to better understand higher derivatives. Consider the function. So we have f of x is equal to x cubed plus 2x squared minus x plus 1. To find the first derivative of f of x, we take the derivative with respect to x. F prime of x is equal to 3x squared plus 4x minus 1. To find the second derivative of f of x, we take the derivative of f prime of x with respect to x. So f second derivative of x is equal to 6x plus 4. To find the third derivative of f of x, we take the derivative of f second derivative of x with respect to x. So f third derivative of x is equal to 6. And finally, the fourth derivative of f of x is equal to f fourth derivative of x is equal to 0. This tells us that after the third derivative, the rate of change of the functions becomes 0. This means that the function itself, it is a polynomial of degree 3, and that's it. You know how to determine the higher derivative of the function. So let's dive into next topic, differentiate function implicitly. This technique is used to differentiate function that cannot be easily expressed in terms of y is equal to f of x or vice versa. Instead, the function is defined implicitly as the intersection of two curves. Let's take a look of an example. So we have x squared plus y squared is equal to 25. We want to find the derivative of y with respect to x. We start by differentiating both sides of the equation with respect to x. D over dx times x squared plus y squared is equal to d over dx times 25. Using the power rule of differentiating, we get 2x plus 2y times dy over dx is equal to 0. Now, we can isolate dy over dx by dividing both sides by 2y. So we have dx over dy is equal to negative 2x over 2y. Now, we will isolate dy over dx by dividing both sides by 2y. So we have dx over dy is equal to negative 2x over 2y is equal to negative x over y. So this is the final answer. Now let's talk about differentiate logarithmic function. To differentiate logarithmic function, we should know the derivatives, the basics logarithmic function. D over dx times natural logarithmic of x is equal to 1 over x. Then d over dx times logarithmic base b times x is equal to 1 over natural logarithmic times b times x. Notice that natural logarithmic of x is equal to logarithmic base e times x is a specific case of the general form of logarithmic base 0 times x where b is equal to e. Since natural logarithmic e is equal to 1, we obtain the same result. Let's take an example. Find the derivative of y is equal to x squared. Notice that both f of x is equal to x and g of x is equal to x above. Take the logarithmic of both sides to get natural logarithmic of y is equal to natural logarithmic of x squared is equal to x natural logarithmic of x. By the product rule, the derivative of natural logarithmic of x is natural logarithmic of x plus 1. So we have 1 over y times dy over dx is equal to natural logarithmic of x plus 1. So, and we replace y is equal to x squared and solve for dy over dx. So we get dy over dx is equal to y over d over dx times natural logarithmic of y is equal to x squared plus 1 plus natural logarithmic of x. And that's all for differentiating logarithmic function.